8-5, rate of change. Rate of change is another way of describing the slope of a line. Today we're going to look at something called direct variation. It's given by the formula y equals kx, as you can see in red just at the top of the slide. And it's read as y varies directly with x. In the equation y equals kx, k is called the constant of variation. It's the rate of change. It's also the slope of the line. Suppose y, in our example here, suppose y varies directly with x. We're going to write an equation relating x and y. We're going to be told that y is 30 when x is equal to -6. So it's a two-step process. And the first step is to find the value of k, the constant of variation. So we have our y equals kx formula. We will substitute in the y at -30 and the x of 6. So we'll have -30 equals k times 6. So -30 equals k times 6. We're going to solve for k, the constant of variation, by dividing both sides by 6. The 6's cancel out, and k ends up equaling -5. We're going to use that now, that k direct variation, constant of variation, k being -5, and we're going to use that to write an equation. We're simply going to substitute it in to the y equals kx formula, and we're going to replace that k with the -5. So the formula we come up with is y equals -5x. So no matter what we find for any other equation relating -30 and 6, we can use -5 as the constant of variation. That works for this particular equation. We will have others that we will see that we do the same thing with. On this next slide, suppose y varies directly with x. We're going to write an equation relating x and y, but this time we're told that y is 7.5 when x equals 10. So we will, step 1, we have to find the constant of variation. So we're going to substitute in 7.5 for y equals k times 10. To solve for k, the constant of variation, divide both sides by 10, and we get k is equal to 0.75. And then in step 2, we have to write the equation, the y equals kx formula. This time we're going to substitute in for the variable k. And we get y equals 0.75x. So direct variation equations. Pretty straightforward, not a whole lot of usefulness by themselves until we put in converting measurements or a real world type example. So the number of centimeters in a measurement varies directly as the number of inches. We need to write a direct variation equation that could be used to convert inches into centimeters. So there's a table in the center of the board that gives the measure in inches in x values. You can see there's a 1, a 2, and a 3 in inches. And then the measure in centimeters, which is 2.54 centimeters, 5.08 centimeters, and 7.62 centimeters. So when x is 1 inch, y is 2.54 centimeters. When x is 2 inches, y is 5.08 centimeters. So we need to come up with a direct variation equation for these. So we have to take our equation, y equals kx, and we're going to substitute in a value for x and a value for y. Generally, it's easiest to select the easiest value available. Please do not select the value that has the 0 in it. Select the next easiest value after that. So we will have 2.54 equals k times the number 1. And, well, we don't really need to divide both sides by 1 because we're going to get k equals 2.54. So that tells us what our constant of variation is with 2.54. Now, in step 2, we write the equation of direct variation, y equals kx, the same equation over again. But this time, we are going to substitute in 2.54 for k. And this equation can be used to find any number of centimeters based on the number of inches. For x, you can take any number of inches you want. Our table only has 1, 2, and 3. You could take 37 inches if you wanted to, substitute it in for x. You'd multiply by 2.54, and it would tell you how many centimeters 37 inches is. So this is a real example of what direct variation can be used for. Your homework is on pages 396 and 397, 10 through 22, the evens.